Hello everyone, Harry here. Welcome to Scrap Science. The story of this video starts with another video. A couple of weeks ago, Tom from Explosions&Fire uploaded a video about synthesizing and showing some pyrotechnics with the perbromate ion. A great video, and you should definitely check it out if you haven't already, but he said something in there that sounded like a challenge to me. What was the exact quote? When discussing methods to make perbromate, he said something along the lines of, there is electrochemistry, but electrochemistry isn't real, it's just a made-up science for wizards. In an effort to avoid electrochemistry, of course, he turns to some cursed noble gas chemistry in the form of xenon difluoride as an oxidizing agent. Again, you should check out the video if you haven't already. But to me, the electrochemistry doesn't sound that hard. Okay, I say this, but to be fair, oxidizing the bromine atom all the way to the perbromate state is one of the most energetically and kinetically unfavorable reactions I can think of. Certainly more difficult than any other oxidation reaction I've ever shown on this channel. Nonetheless, I think we can do it. We can make this ion that scarcely exists, and we can do it with a simple electrolytic oxidation. Now, given that the formation of the perbromate ion is so unfavorable, we kind of need to pull out all the stops. We'll start with this super pure sodium bromate that I made in a previous video, and we'll be oxidizing it using the best electrode material I can think of to perform aqueous oxidations like this. This here is my sample of boron-doped diamond. I got this electrode material a year or two ago, and I've shown it a couple of times, I think. The special thing about this electrode is that it is so ridiculously terrible at oxidizing water. So terrible that we can actually do oxidation reactions in aqueous conditions that exist far beyond the standard potential of the oxidation of water. Other electrodes, of course, are more limited in the fact that if you push the potential too high, you just get water oxidation. This material hinders water oxidation so much, enough such that we can actually perform the very difficult oxidation of bromate to perbromate in aqueous conditions. If you'd like to know more about this electrode, I have a whole other video on that. Now, I'm not expecting this to work that well, and I'm certainly not expecting a big yield, but if we set up an H cell, fill our anode chamber with bromate solution, our cathode chamber with whatever, sodium hydroxide solution and a nickel cathode, I suppose, and use a naphthion membrane to keep the bromate in our anode compartment, we should get some perbromate if we absolutely crank the voltage. So, I'll go and set that up now. With the experimental setup exactly as described, sodium hydroxide solution with a nickel cathode in the left-hand chamber, sodium bromate solution with a boron-doped diamond anode in the right-hand chamber, I guess it's time to start running the cell. – 200 milliamps. Seven days later, we've run this cell for long enough that if even 1% of the charge that went into this went towards making perbromate, we will have made a reasonable enough quantity that it should be extractable. I think we've left it running long enough that doing an extraction now will well and truly tell us whether or not this process is actually working. So now, 3 beakers here. On the left, we have the sodium hydroxide solution that was generated in the cathode compartment of our cell. I'm going to put that to the side because that is not important. And then here we have our electrolyte from our anode compartment. This started out as 16 grams of sodium bromate in solution, and hopefully under the oxidizing conditions on the boron-doped diamond surface, at least a small part of that has been oxidized into sodium perbromate. Now, there's not much literature on actually extracting perbromates or even the properties of perbromate salts in general because, again, they're very, very hard to make. So on the right here, I've prepared another solution of 16 grams of sodium bromate. That's still dissolving, but what we'll basically do is we'll do the same extraction technique on both of these. This one has not undergone electrolysis, this one has. If we have truly made sodium perbromate in this solution, extracting it from here will yield a product, and extracting it from here will yield nothing. And that's basically how we can be sure that we've actually done something to that solution. This is our control. Now, luckily for us, there's one thing that is known quite well about sodium perbromate, and that is the fact that it is soluble in acetone, whereas all of the other bromine-based species like sodium bromide, sodium hyperbromite, or sodium bromate are all pretty much completely insoluble. So to do our extraction, the method will be, we just boil these solutions down to dryness, and then we'll do an acetone extraction on the solid residue that's left behind, and then we'll get rid of the acetone. I don't have particularly high hopes, but let's try it out. Now, moment of truth. After the acetone extraction and evaporating off all of the acetone, starting with our control, the sodium bromate that we just kind of dissolved up and then didn't electrolyze, the acetone extraction was able to get absolutely nothing, as we expect. Even if we look very closely, I can't see any residue left behind there, so we can be confident that the acetone didn't extract anything from our control. Now for the cell, extracting things with acetone gave us, there's something there. There's really not much though. In fact, I would say whatever residue that is, I can't measure the mass of that with my scale because there's just not enough there. It might be perbromate, but man, there's really not much of it. Let's put them side by side actually. Yeah, there's definitely a difference there. So, I don't 100% know whether what we've made here is perbromate or whether this is just some other byproduct of the cell that we were able to extract with the acetone. But regardless, obviously, if it took a week of work to make this quantity, which again, I genuinely can't measure, really not a practical way to make perbromate salts, obviously. Now that we've concentrated it down, I do really want to know whether this is actually perbromate. And there's one other test I can think of that we can actually perform on this to see whether it was, at least in part, successful. And that test is the methylene blue test. The methylene blue test is really common when we're making perchlorate salts. If you have perchlorate in a solution, if you add just a single drop of methylene blue to it, the perchlorate ions will form a solid purple complex. It's a rather selective test for the perchlorate ion, and as you might expect, we do expect it to do the same thing with the perbromate ion. I found one source in literature telling me that it does do the same thing. So let's give that a go. Hey, it did do that. Okay. evidence does suggest that we may have done it, just to a very small degree. I'll be honest, I was not really expecting that that would give that result. That is definitely a solid purple complex floating around in there. Of course, controls are important too. So on the right now, I have just a solution of regular old sodium bromate. We do our 1 drop of methylene blue. Yeah, you can see that doesn't form a solid and it doesn't go purple. I'm going to be honest, I think we have done it. We made a detectable amount of sodium perbromate. I was going to leave the video there. It's actually been a couple of months since I did the methylene blue test. And while the methylene blue test definitely did show that we have a perhalogenate ion, I really would like to be more sure that this is perbromate, because it is kind of feasible that we could have had a bit of chloride contamination in our sodium bromide starting material, and feasibly that could have become what we are thinking is our final product of sodium perbromate, but it's actually the trace amounts of chloride that we started with turned into sodium perchlorate. Having thought about this for a little while, there is actually a test that we can do to check whether we have sodium perchlorate or sodium perbromate. Both ions are generally extremely inert, but perbromate is ever so slightly more reactive than perchlorate. Whilst there are very few situations where the perchlorate ion will actually act as an oxidizer in solution, there are a few situations where the perbromate ion will do so. So the test that I've set up here exploits that. What I have is a situation where the perbromate ion will react to oxidize something, but the perchlorate ion will not. Inside these 2 test tubes that I've got just heating in a hot water bath is some concentrated phosphoric acid with a small amount of manganese sulfate added to it. In theory, if we add a drop or 2 of sodium perchlorate solution to the left test tube, there should be no reaction. The perchlorate ion should not be able to oxidize the manganese ions in solution. However, on the right, if we add just a couple of drops of our actual product from this cell, what is hopefully our perbromate, the perbromate ion should actually be able to oxidize the manganese ions in there and give us a kind of black or purple, maybe violet color. There should be quite a clear difference between these 2 test tubes if what we have is what we think it is. So starting with adding a bit of sodium perchlorate to the left test tube, again we should see no reaction here. We do need to wait a couple of minutes, but I'm pretty sure we should see no color change there. And of course, the thing we really want to see is the perbromate, so I'm going to add that to the right test tube right now. Man, it is faint, isn't it? I can see a difference there though. Right, can you see that kind of pink, purplish color? I assume it is the permanganate ion that is generated by the oxidation of manganese 2+ by the perbromate ion. I was trying to be really skimpy with the amount of perbromate I had to add to make this test work. Maybe I'll add a bit more so that you can see this more clearly. Really burning through my product here. Just a tiny bit more. Look, if I had more product, I would use more of it for this test, but I think that's pretty clearly a little bit more pink than the one that I only added sodium perchlorate 2. Now, is this conclusive proof that we do have the perbromate ion? Did we actually do it? Well, I don't personally have access to anything remotely close to elemental analysis, so I can't say for absolute certainty, but as far as I'm concerned, I am actually convinced that what we have here is the perbromate ion. It seems to have passed every test I've decided to throw at it, so again, I am satisfied with this conclusion. We may have only ended up with, a milligram or less of product, but we were able to do it, I think. If you're not convinced, please let me know in the comments what other tests I can do with a very small amount of perbromate that would convince you that that's what I've made today. If you know of any other tests, please let me know, because I'm working with a pretty limited amount of literature right now. Anyway, with that all kind of concluded, I might head off and put the rest of my product in an ampule for safekeeping, I think. You can really see how little we have left after all those tests. See you later.